They hand-dug a 1,000-foot deep crack in Utah. At first glance, the phrase sounds impossible. A crack is something nature creates, not people. Yet in the remote badlands and plateaus of eastern Utah, miners spent decades descending into nearly vertical fractures that sliced through the earth like giant knife wounds. They followed black walls of solid hydrocarbon deep underground, using little more than pneumatic drills, timber supports, rope systems, rails, and raw endurance. Some of these shafts reached depths approaching 1,000 feet, or roughly 300 meters, inside narrow geologic fissures formed millions of years earlier. The miners did not create the cracks themselves. Nature did that. But they carved human access into them by hand, turning ancient tectonic fractures into some of the strangest mines in North America. How does a crack stay nearly vertical for miles without collapsing? Why would hydrocarbons harden into a solid mineral instead of remaining liquid oil? What geologic event injected black resin into fractures across an entire basin? And why does this material exist in commercial quantities in only one place on Earth? The answers lie inside the geology of the Uinta Basin of northeastern Utah, one of the most unusual petroleum systems ever studied. The story of Gilsonite, scientifically known as Uinta, is not simply a mining story. It is the story of deep burial, tectonic stress, hydrocarbon migration, fracture mechanics, basin uplift, volatile loss, and the transformation of liquid petroleum into a brittle black solid trapped inside giant vertical veins. The landscape where Gilsonite occurs does not immediately look like the center of a rare hydrocarbon phenomenon. The Uinta Basin is a broad structural depression bordered by the Uinta Mountains to the north and the Tavaputs Plateau to the south. Today, the region appears dry and rugged, with mesas, cliffs, and dusty valleys, but its geology records repeated cycles of mountain building, inland seas, lake systems, sediment burial, and tectonic deformation extending back hundreds of millions of years. The foundations of the basin began forming during the late Cretaceous and early Paleogene periods, when compressional tectonic forces associated with the Laramide orogeny reshaped much of western North America. The same tectonic episode that raised the Rocky Mountains also warped the crust across present-day Utah and Colorado. Instead of producing only mountain ranges, the compression created adjacent structural basins where enormous thicknesses of sediment accumulated. The Uinta Basin became one of those sediment traps. Rivers flowing from surrounding uplifts carried sand, mud, clay, and organic debris into the subsiding depression. Over millions of years, the basin filled with layered sediments that eventually reached several miles in thickness. Organic, rich environments developed repeatedly, especially during the Eocene epoch when large freshwater lakes occupied much of the region. Among the most important formations was the Green River Formation, famous for its extraordinary organic content. The Green River lake system was unlike most modern lakes. It persisted for immense spans of geologic time and accumulated enormous quantities of algae, microorganisms, plant matter, and fine sediment under conditions that often limited oxygen at the lake bottom. Low oxygen conditions slowed decomposition, allowing organic material to accumulate faster than it decayed. As these sediments were buried deeper, heat and pressure gradually transformed the organic material into kerogen, the precursor to petroleum. Continued burial pushed temperatures higher, eventually generating liquid hydrocarbons. In most petroleum systems, these hydrocarbons migrate through porous rocks and accumulate in underground reservoirs. In the Uinta Basin, however, part of the system behaved very differently. At some point after petroleum generation began, tectonic stresses fractured large portions of the basin rocks. These were not random cracks. The fractures formed in organized sets controlled by regional stress fields. Many became steeply vertical and remarkably continuous. Some extended for miles across the basin, while maintaining widths ranging from only a few inches to several feet. Modern mapping identifies more than 70 major Gilsonite veins across an area roughly 100 kilometers long and 50 kilometers wide. The geometry of these veins remains one of the most striking features of the deposit. Unlike coal seams, which are usually horizontal because they formed from ancient peat layers, Gilsonite veins cut vertically through surrounding rock formations. They resemble giant injected dikes rather than sedimentary beds. Geologists studying the veins concluded that the fractures opened under tectonic tension, probably during phases of regional uplift and crustal adjustment, after hydrocarbon generation had already begun. Once fractures opened, hydrocarbons migrated upward into them from deeper source rocks. This migration likely occurred under high fluid pressures. Petroleum systems naturally generate pressure during burial, because organic matter transforms into liquid and gaseous hydrocarbons that occupy more volume than the original material. If pressure exceeds the strength of surrounding rock, fractures can propagate upward. In the Uinta Basin, the fractures acted like vertical plumbing systems. The hydrocarbon that entered these cracks was probably very different from modern gilsonite. It was likely a heavy proto-petroleum rich in asphaltic compounds, resins, nitrogen-bearing molecules, and volatile hydrocarbons. Over time, the lighter components escaped. This process is critical to understanding why gilsonite hardened into a solid. Petroleum is not a single substance. It is a mixture containing molecules with different sizes, weights, and boiling characteristics. Lighter hydrocarbons evaporate or migrate more easily, while heavier compounds remain behind. When petroleum becomes exposed to pressure changes, fractures, groundwater interaction, or surface-connected pathways, the lighter fractions can gradually disappear. What remains becomes progressively thicker and more viscous. In the case of gilsonite, geologists believe the hydrocarbons trapped inside the fractures underwent extensive devolatilization over millions of years. Lighter oils and gases escaped through the fracture systems while the remaining heavy asphaltic material solidified into a brittle, glossy black substance. The result was not coal and not conventional asphalt, but a unique naturally occurring hydrocarbon resin with extremely high purity. The chemistry of gilsonite makes it unusual among solid hydrocarbons. It contains a complex mixture of high molecular weight hydrocarbons, along with nitrogen-bearing compounds, and relatively low sulfur content compared with many petroleum residues. Its low ash content and purity allowed it to be used directly in industrial applications without large-scale refining. That characteristic became economically important because the ore could simply be mined, crushed, graded, and shipped. Yet the same chemistry that made gilsonite valuable also made mining dangerous. Gilsonite is brittle and easily fractured. Underground workings frequently generated fine dust particles, and hydrocarbon dust suspended in air can become explosive under the right conditions. Early mines in Utah suffered repeated fires and explosions, especially during the late 19th and early 20th centuries. Timber supports, poor ventilation, open flame lighting, and limited dust control created hazardous conditions underground. The geometry of the veins compounded those hazards. Traditional mining methods evolved mainly around horizontal deposits like coal seams or metal ore bodies. Gilsonite veins instead forced miners to work inside steep vertical fissures. Some shafts followed the veins downward almost like elongated chimneys descending into darkness. Imagine standing inside a crack only a few feet wide but stretching hundreds of feet upward and downward. The walls are black and glossy, timber braces creak under stress, dust hangs in the air. The deeper miners followed the veins, the more complicated the engineering became. Because the veins were nearly vertical, miners often used methods resembling shrinkage stopping or vertical vein extraction. They blasted or cut material from the vein walls while standing on accumulated broken ore beneath them. As ore was removed, platforms and ladders descended deeper into the fracture. Ventilation became increasingly difficult with depth because the narrow geometry restricted airflow. Water infiltration also posed serious challenges. Fractures naturally act as pathways for groundwater movement. Even in arid regions, subsurface water can migrate through joints and faults. When water entered gilsonite workings, it destabilized timber supports, increased rockfall risks, and complicated transport systems. The surrounding rocks added another layer of complexity. The veins cut through sedimentary formations with differing mechanical properties. Some layers were relatively competent sandstones capable of maintaining stable openings. Others consisted of weaker shale or mudstone prone to sloughing and collapse. Stress redistribution around mined openings could trigger localized failures, especially where bedding planes intersect the vertical fractures. The mines therefore became practical laboratories in structural geology. Miners unknowingly observed fracture propagation, rock mechanics, and stress behavior every day underground. Veins sometimes narrowed abruptly, split into branches, or terminated against faults. In some locations, they widened dramatically into ore chutes where hydrocarbons had accumulated more heavily. These variations reflected the original fracture dynamics that controlled fluid migration millions of years earlier. One of the most remarkable aspects of the deposit is how straight many veins remain over long distances. This reflects the physics of fracture propagation in brittle rock. When crustal stresses exceed rock strength, fractures tend to extend perpendicular to the least principal stress direction. Under relatively stable stress fields, fractures can maintain consistent orientation for great distances. In the Uinta Basin, the regional tectonic setting likely produced strong directional stresses that guided fracture formation. Many Gilsonite veins trend northwest-southeast, indicating consistent stress orientations during emplacement. Their steep vertical nature suggests the fractures opened under horizontal extension or differential tectonic stress after significant burial had already occurred. The veins themselves are often interpreted as clastic or hydrocarbon-filled dikes. In igneous geology, a dike forms when molten rock intrudes into fractures. Gilsonite veins behaved similarly, except the injected material was hydrocarbon-rich fluid rather than magma. Pressure forced the material upward into open fractures where it later solidified. This injection model explains several unusual characteristics. It accounts for the sharp vein boundaries, cross-cutting relationships, and vertical continuity. It also explains why the material differs chemically from conventional reservoir oils. Once trapped inside fractures, the hydrocarbons experience prolonged alteration and loss of volatile components. Modern geochemical studies support this interpretation. Biomarker analysis links gilsonite to petroleum generated from organic rich lacustrine source rocks associated with the Green River Formation. Isotopic signatures also indicate petroleum origins rather than coalification processes. In other words, gilsonite is essentially a naturally upgraded solid petroleum concentrate formed through geologic filtering and alteration. The isolation of the deposit to northeastern Utah further emphasizes how unusual the required conditions were. A rare combination of factors had to align precisely. First, the basin needed extraordinarily rich organic source rocks capable of generating vast amounts of hydrocarbons. Second, tectonic stresses had to create extensive fracture networks. Third, hydrocarbons needed sufficient mobility and pressure to invade those fractures. Fourth, the system required long-term volatile escape without complete destruction of the remaining material. Finally, uplift and erosion had to expose the veins close enough to the surface for mining. Remove any one of those steps, and the deposit probably never forms. The uplift history of the region played a major role in preservation and exposure. As the Colorado Plateau and surrounding regions rose during the late Cenozoic, erosion stripped away overlying sediments and gradually revealed the fracture systems nearer the surface. This uplift also changed subsurface pressure conditions, possibly accelerating volatile loss from the hydrocarbon-filled veins. Erosion exposed portions of the veins at the surface where prospectors first discovered them during the 19th century. Some veins appeared as dark linear ridges cutting across lighter-colored rock. Others weathered into trenches, because surrounding rocks eroded differently than the resistant hydrocarbon material. Early miners quickly recognized that the veins could be followed underground. Unlike diffuse oil accumulations, gilsonite occurred in concentrated masses with clear boundaries. The challenge was not locating tiny scattered pockets, but safely extracting material from deep, narrow fissures. Mining technology during the early years remained relatively primitive. Workers used hand tools, black powder, picks, shovels, and simple hoisting systems. Because gilsonite breaks easily, miners could often detach large pieces without extensive blasting. Cloth sacks carried ore to the surface where it was loaded onto wagons. Transportation itself became a geologic problem because of the basin's rugged terrain. The Uinta Basin is surrounded by difficult topography carved into plateaus, canyons, and steep escarpments. Moving ore across these landscapes required routes capable of crossing structurally uplifted terrain shaped by millions of years of erosion. The later construction of the Uinta Railway represented an engineering adaptation to geology. Rail routes had to navigate unstable slopes, deeply incised canyons, and variable sedimentary rock conditions. Maintaining tracks across such terrain proved difficult and expensive. Landslides, erosion, and harsh weather continuously threatened infrastructure. Even the later slurry pipeline reflected the unusual properties of gilsonite. Most mined minerals require crushing, smelting, or chemical refinement. Gilsonite instead could be pulverized and suspended in water for pipeline transport, because the product itself already possessed desirable industrial chemistry. The pipeline crossing the Tavaputs Plateau effectively transformed solid hydrocarbon mining into a fluid transport operation. Despite technological improvements, the underground geometry of the veins never stopped presenting hazards. The deeper miners descended, the more rock stress increased. At depths approaching 1,000-foot deep crack in Utah, or about 300 meters, surrounding rock pressure becomes substantial. Narrow vertical excavations concentrate stress unevenly around openings, increasing risks of spalling and localized collapse. Temperature conditions also change with depth. Earth's geothermal gradient means rock temperatures generally rise downward. Although the gradient varies regionally, miners working several hundred meters underground encountered noticeably warmer conditions. Combined with limited ventilation and hydrocarbon dust, the environment became physically demanding. The veins themselves preserved evidence of ancient fluid behavior. Some displayed banding, brecciation, or internal textures indicating multiple injection phases. In places, fragments of surrounding rock became trapped inside the hydrocarbon material, suggesting repeated fracture opening and sealing events. These textures are valuable because they record the dynamics of subsurface fluid migration. Modern structural geologists view the Gilsonite system as an example of fracture-controlled hydrocarbon emplacement. Rather than accumulating passively in porous sandstone reservoirs, hydrocarbons actively invaded tectonic fractures under pressure. This makes the deposit important not only economically but scientifically, because it provides direct evidence of petroleum migration pathways. The deposit also reveals how brittle deformation affects fluid systems in sedimentary basins. Fractures dramatically increase permeability compared with intact rock. Even low porosity formations can become effective conduits when fractured. In the Uinta Basin, tectonic stresses effectively rewired subsurface fluid flow by opening vertical migration pathways through otherwise layered sedimentary rocks. Some researchers compare the process to hydraulic fracturing occurring naturally over geologic timescales. In modern industrial fracking, pressurized fluids create artificial fractures that allow hydrocarbons to move. In the Uinta Basin, natural overpressure likely produced similar effects without human intervention. Hydrocarbons themselves may have contributed to fracture propagation by increasing pore pressure until rocks failed. The extraordinary vertical continuity of the veins also raises questions about sealing mechanisms. Why did hydrocarbons remain trapped instead of escaping entirely to the surface? The answer probably involves episodic fracture opening. Fractures may have opened during tectonic pulses, filled with hydrocarbons, then partially sealed through mineralization or stress changes before reopening later. This intermittent behavior could trap large volumes while still allowing gradual volatile escape over millions of years. The resulting material became increasingly solid with time. Gilsonite today fractures with a shiny conchoidal surface somewhat resembling obsidian. That brittleness reflects its highly evolved hydrocarbon chemistry. Unlike softer asphalt deposits, gilsonite behaves more like a hard resin. Its industrial usefulness stems directly from those properties. The material dissolves in hydrocarbons and organic solvents, blends well with petroleum products, and improves durability in inks, coatings, drilling fluids, and asphalt systems. The same molecular structure created through geologic alteration millions of years ago now determines modern industrial performance. Yet the geological story remains the most remarkable aspect. A basin accumulated organic rich sediments in ancient lakes. Burial transformed that organic matter into petroleum. Tectonic forces fractured the crust. Pressurized hydrocarbons invaded vertical cracks. Millions of years of volatile loss hardened the material into glossy black veins. Erosion exposed the fractures near the surface. Humans then descended into those ancient tectonic wounds and mined them by hand. That is what people mean when they say miners' hand dug a 1,000-foot deep crack in Utah. They were descending into a fossilized plumbing system of the earth. Every foot downward represented a journey through interacting geologic processes, sedimentation, burial, hydrocarbon generation, tectonic stress, fracture propagation, fluid migration, uplift, and erosion. The mines existed because all of those processes aligned in exactly the right sequence. Even today, geologists continue studying the veins because they offer insights into petroleum migration and fracture mechanics that are difficult to observe elsewhere. Most hydrocarbon pathways remain hidden deep underground. In Utah, nature preserved the pathways themselves as solid rock. The black veins cutting through the Uinta Basin are therefore more than mining targets. They are physical records of a petroleum system frozen in place. They show where fluids moved, where pressure built, where rocks fractured, and where tectonic forces opened conduits through the crust. And deep underground, where miners once followed those vertical walls into darkness with drills and lanterns, the Earth still preserves the geometry of an ancient geologic event that transformed liquid hydrocarbons into one of the rarest mineral deposits on the planet.